So okay, now that we have our algorithm mostly done, it's time to think about the base case. So one cool thing about the counting algorithm is the base case is built in. So the base case is a leaf, and you'll notice for a leaf, they have no children. And so that sum is really going to be a sum over the empty set, and so be 0. So we get the count of v will be 0 plus 1, which is 1, which is exactly the count of the subtree for a leaf. So the base case is actually baked into this equation, which is really nice. On the other hand, for the overall algorithm, the base case is built into that fact that v eventually stops, or v will eventually be a central vertex. And really, we could see that as the leaf case in the full proof. So that's the algorithms, and now let's consider the proofs. So the formal proof requires a lemma that says if v has at most n over 2 nodes in its parent subtree, then either v is central or there exists a central vertex in a subtree, or let's just say in V's subtree. Okay, and this is what we're going to prove by induction. Specifically on the height of node V. So the base case this is when V is a leaf. So let's call the height h. When h equals 0, V is a leaf. And we know leaves can never be central vertices. Specifically, V cannot have a small parent subtree. So what does this mean? Well, V doesn't even satisfy the assumption up here. We are assuming V has this property. And so the base case is vacuously true. The statement doesn't even apply to such a V. Okay. Let's look at the inductive step. So now we're assuming we're somewhere in the tree and we're not a leaf. So we know V has some parent subtree, which by assumption has at most n over 2 nodes. And we know V has some children. And I'm drawing this with 3 nodes, but technically the problem's for binary trees. But it's not super important. Okay, so we have V here, and we have its 2 children. And we want to prove either V is central. So if V is central, we're done. So let's just assume it's not central. So V is central, done. We've found a central vertex, so assume V is not central. So if V is not central, then we know there's some subtree. Let's say it's this one, W, with greater than n over 2 nodes. And now that subtree has smaller height, and it has smaller height just because of how trees work. It can't have a higher height than its parent. So now we can apply the induction hypothesis on W. So in particular, we know either W is central or W. Well, before we even get there, we need to make sure we can apply the statement. So notice we have, again, we need to make sure that there are not too many nodes in this upper tree. And this follows by the same argument before. If this subtree has at least n over 2 nodes, then all of these can be at most n over 2, because there's only n nodes in the graph. So what does this mean? It means W is also a node that's satisfied by the lemma, and we know W has smaller height. So by the induction hypothesis, we know that W, or in the W subtree, so in this subtree, somewhere in there exists a central vertex. Now, if there exists a central vertex in that subtree, well, this subtree is also a subtree of V. So this implies that same node is a central vertex. So in the subtree, TW, TV. And that's proof. So if V was central, we're done. Otherwise, we have to find the central vertex deeper in the tree. And that's exactly what the algorithm's doing too. So once again, we see an example of where the proof and the idea behind the proof is the same as the idea behind the algorithm. So we generate the algorithm and proof, or at least the proof idea, at the same time. We kill two birds with one stone. And by doing this, by consciously trying to think of the proof while we come up with the algorithm, we're also going to make sure our algorithm's really correct. We're not missing out on any edge cases. So that's the lemma. Now technically, if we want to be totally good, we also have the full theorem, which says any tree has a central vertex. Now, why is this true? Well, we're going to apply the lemma. So remember, the root has 0 nodes in its parent subtree. So by the lemma, either the root is central or the central vertex is somewhere in the subtree, in the root subtree. But the root subtree is the whole tree. Okay? So that's the full proof that central vertices exist. And so this implies, together with our argument before, that the combination of these two algorithms is truly correct. And they're fast, O of n time. This is also an example kind of a reduction, because we reduced the problem of finding central vertices to the problem of counting number of nodes in subtrees.